So let's continue to discuss, the quantum mechanics of the spin half. So last time we know that if you have this Stern-Gerlach experiment, right? Suppose you have SGZ, right? For example, that means basically you have a magnetic field like this one, and the spins will be split into two, right? Into two axes. So this is in the z direction, okay? And then we have the states or possibility of this output. So one possibility, we call this one spin up or in the z direction, okay? You can also denote this as say chi z if you use a matrix form, and this is 1, 0, okay? You can have, for another possibility, you have this spin down, and that is z bar direction, okay, or chi z bar, chi z bar, okay. So this is 0, 1, okay, and this form also a normal basis of 2D Hilbert space. Right. So this is for the measurement in the z direction, okay. But you can also have the SCX, for example, okay. You have something like this one, for example, and then this one will also give us two possibilities. One of this one is called the spin right, okay, or in the x direction. And this one actually can be written as superposition of the spin up and spin down states. Right. And another state is another possibility, okay, it's called a spin left, or in the minus x direction. We denote it as x bar, right? Which should be also orthogonal to the x state. It's also a superposition of this spin up and the spin down state, okay? And of course, you can also have the z direction as a y direction, okay? Say like this one. And then you have the y state. We can call this one the spin in state, chi y, and that's the matrix like this one, right? It's also a superposition of up and down states. So the difference you can see that is there's a phase factor if we compare this to the states in the x direction. Okay, so that's another possibility. But so these are the states corresponding to the possibilities of the Stern-Gerlach experiments in the z, x, and y directions. Okay. Of course, you can also have a state in any direction. So we can denote a state, say m, in the n direction, or use Euler angles theta phi to denote this direction. And this one can be written as e to minus I phi over 2 cosine theta over 2 spin up plus e to I phi over 2 sine theta over 2 spin down, right? And that one in the matrix form is e to minus I phi over 2 and cosine theta over 2 e to I theta phi over 2 and sine theta over 2, right? And this theta takes values from 0 to pi, and phi takes values from 0 to 2 pi. Okay, and they are just Euler angles. Okay, and this m actually is the direction corresponding to these Euler angles. So it's sine theta, cosine phi, that's the x component, and sine theta and sine phi, the y component, and the cosine theta. Right. So you can use right. So this is the z, x, and the y direction. So you can have a direction, specified by this Euler angle. Right. So this is theta. And this is phi. Okay. Right. To denote the state of this. So this vector is called the Bloch vector. Okay. Right. So that is the general states that we can have in this two-dimensional Hilbert space, corresponding to the experiment that we have two possibilities, right? So basically, a spin half, we call this one a spin half state, is a superposition of two possibilities, right? Okay, or two orthogonal states. Okay, so this is the states. Okay, correspondingly, you have a 2D Hilbert space. Okay, right. So that's a state, and then for the operator, right? For the operator, we have right. So it should be 2 times 2, which is omission. Right. So it can be always any operator must be written as H0 sigma 0 plus Hx sigma x plus Hy sigma y and then plus Hz. Okay. With these Pauli matrices, okay, sigma 0 is just a unit. Okay, and sigma x and sigma y, they are all omission operators. Okay, so these are the Pauli matrices. Okay, so they are 2 times 2 omission, and they're also unitary. Okay, and they satisfy a very important, okay, commutators. That's sigma x and sigma y equals to 2i sigma z. Okay, right. So this one, and also the cyclic permutation. Okay, right. So that's very similar to the angular momentum we had before. So we can also define the operators x, y, and z. Okay, equals to h bar over 2 times sigma x, y, and z. And then from this one, immediately we obtain the the commutator between Sx and Sy, that will equals to I h bar Sg. So this is very intriguing, right? Of course, and there are cyclic permutations, right? So this is the same as L, right? So that's why we can interpret thus we can have this one equals to as the angular momentum operator of a spin half. Okay. And also we found that they actually have the eigenstates, very intriguing as well. So sigma x acting on x equals just to x. Sigma x acting on x bar just equal to minus x bar. And sigma y acting on y equals to just y. And sigma y acting on y bar just equal to minus y bar. And sigma z acting on z, of course, just z. And sigma z acting on z bar just equal to minus z bar. Right. So that means, you know, the Pauli matrices is just the same as this magnetic dipole. Because remember this x bar, for example, just you know, possibilities, the possible states for mu x, right? So when we measure the magnetic dipole moment along the x direction, so we actually, so if we go back to the definition of the states, right? So remember this is the definition of states. So you can take this one, for example, as just the possibilities of measuring mu z, right? And this one is just the possibilities of mu x, and these are the possibilities of mu y, right? So that's but this one are also eigenstates. So they're also eigenstates of the Pauli matrices. Okay. Right. So that means we can actually just simply write down this dipole operator that equals to, you know, a constant called Landau G factors times mu b times you know, this S operator divided by h bar, right? And this one is obtained from by comparison with the semi-classical results for the orbital momentum, right? Remember, if we have the orbital momentum, then we have a magnetic dipole moment that equals to mu b times L operator over h bar, okay? And this GE actually was measured equals to 2.002 3 something, okay, with very high efficiency. It's not a 1, first of all. Does not equal to 1. That's one thing, okay. And so this is already an indication of non-classical origin, okay. So we will come back to this point a little bit later when we got more information about this spin, okay. But at this point, we are ready to answer questions. Someone of you maybe say that we call this one spin half, right? The question is, why half? Why do we call this one spin half, not spin third, not spin 1, not spin 2, right? Okay, now let me show you. So remember, in the orbital angular momentum, once we have this one, that equals to L squared, right? So this one also always take a value to be L times L plus 1 times h bar squared, with L equal to 0, 1, 2, and so on and so forth, right? So now we say that we interpret the S, and then we look at we take this S as angular momentum. And so we also would like to check the S square, see what's the results, what's the possible eigenvalues of this S square. And this one, of course, equals to h bar over 2 times sigma x squared plus sigma y squared plus sigma z squared. And this one should also be squared, right? But we already know that this sigma x, sigma y, sigma z, the Pauli matrices, they are emission and they are unitary, so the square must be 1, right? So sigma x squared equals to 1, sigma y squared equals to 1, sigma z squared equals to 1. So 1 plus 1 plus 1 is just 3. So the result is just 3 over 4 times h bar squared. So it does not equal to any L times L plus 1 times h bar squared if L is an integer number. But this one can be written as 1 over 2 times 1 over 2 plus 1 times h bar squared. So that is very intriguing. So that's why. So as if the total angular momentum is S equals to h bar over 2. This is a half quanta, right? Half quantum of action. And we know that for the orbital states, and the action is always quantized as an integer number multiplied h bar. But now for this spin, we have a half integer. We have half quanta, okay? So this is probably the first fractional quantization, okay, in physics, right? You don't have an integer number, you have a half of quanta, okay? And this one actually is a very interesting and intriguing results for the spin, okay, physics. And so later on, when we study quantum mechanics 2 in next term, we're going to learn more deeper meaning of this half quantization, okay? All right. So that is one thing that we have learned a little bit. And then, of course, you wonder the Hamiltonian will be what? Okay, we know that if we have a magnetic field, okay, so in the magnetic field, the magnetic dipole mu, sorry, has energy that is minus mu dot b, right? Now we have quantum mechanics, so that we obtain the result. The Hamiltonian just equals to minus the mu operator of this magnetic field. That is just minus E mu B and S dot this B and divided by H bar, right? So this is the Hamiltonian that we have for the spin half, okay? Right. Sometimes we can just simply write down this as B dot S, okay? Right. So that this B, the dimension of this little b, is the dimension of time to -1, okay? Right. So that since this S has dimension is just H bar, that's energy and the T, right? So I have the correct dimension. So this one is something like a frequency, right? It has a dimension like a frequency, okay? So that is the Hamiltonian, okay? Right? Okay, so now we can look at this eigenstates. For example, let's take this B just along the direction Z, right? And then this Hamiltonian will just equals to this B Z times sigma Z. That will equals to BZ minus BZ. That is very simple, right? So the eigenstates, you have spin up and spin down the divided by H bar over 2, sorry, eigenstates. And the H bar BZ over 2 minus H bar BZ over 2 are the respective energy, right? Okay. So this is the simplest case, okay? Right. And then, of course, if you have, so this is one example. You can also consider another example. So H equals to Bx and sigma x. That will equals to H bar over 2 times Bx 1100. You know that the x and x bar are the eigenstates, right? Energy will be H bar Bz over 2, H bar Bz minus over 2, right? Okay. So these are the states. As an exercise, let me, you can do something like this one. You can find that if you have a Hamiltonian, that equals to B times M dot S. So this is H bar over 2. That have the correct dimension. Right. So that equals to you find this one, and then actually you got two states. One state is M, another state is minus M. Okay, and the eigenvalues will be H bar B over 2 and H bar B over 2. That's minus sign. Okay, so you can check this for yourself. Okay, so that means if you have the magnetic field in this direction, this is B. Okay, and then the Bloch vector so this is the state M, okay? And this one is the state minus M, okay? So they are the two eigenstates of this Hamiltonian, okay? With two eigenvalues to be H bar and B and minus H bar B over 2. So this is the homework problem actually. It asks you to check whether this one is correct or not, okay? All right. now to explore the more meaning of this state, this kind of space states. So we would like to suppose that we have a state and we want to measure and different dipole moments, or simply we just measure sigma x and y and z, right? The Pauli operators, and see what would be the outputs. Let's consider state, say m. That's theta phi. So we are now interested in the quantum measurement. Okay, let's consider state m. That's given by two angles that equals to e2 minus I phi over 2 cosine theta over 2 spin up plus e2 I phi over 2 sine theta over 2 spin down, right? We know that this state is given by this vector specified by the Euler angle theta and phi, right? And this m equals to sine theta cosine phi, sine theta sine phi, and cosine theta. Right, so that's the unit angle, right? Unit direction, okay? It's the Bloch vector. Okay. So we want to measure this one. Okay. Say, for example, if we want to measure sigma z, right? The sigma z has two eigenstates. That's up and down. Okay. So now you have the coefficients, and this m actually can be written as c up and up, c down and down, right? Okay. So let's check this according to the measurement postulate. So we're going to have outputs. That will be +1 or -1, right? Randomly. So what was the probability? So p plus we just equal to c up modulus squared. So which is just this term, right? So that's nothing but just cosine squared theta over 2. And this one can be written as 1 minus cosine theta, 1 plus cosine theta divided by 2, right? And another one, of course, is just c down modulus squared. That's sine theta over 2 squared. Okay, and that's of course just 1 minus cosine theta over 2. And you can see that this is 2. So you can see that p check p plus plus p minus is equal to 1, right? Okay. So what's the expansion value? That's of course will be +1. That's one possible output, right? Times this probability, and plus another output times another possibility, right? So this will be, just p plus minus p minus. That is nothing but just cosine theta. What is the variance? To look at the variance, we need to consider this one, right? But this one is nothing but just m times sigma z squared and m squared, right? And m. But sigma z squared just 1. So the average of 1, of course, is just 1, right? Okay. So then what's the variance? So that's sigma z squared averaged minus sigma z average squared. So this will be just 1 minus cosine squared theta. Right. So if we plot this as a function of theta from 0 to pi, okay, you look at the variance. So you can see that the variance actually, if theta is 0, this is 0. If theta is pi, it's also 0. And in between, okay, the variance actually goes like this one. Right. So this is the variance. So what's this state? This state is nothing but just a spin up state. So it's the eigenstate. Of course, the eigenstate is a state that the sigma z has a certain value, so that it has a 0 variance. And this state is just spin down state. It has no variance as well, right? Because it's also eigenstate. In the middle, that has a maximal, you know. Okay, if theta is something like a pad, and this one, this m, okay, will be, this n will be in the xy plane, right? So you can see that it's perpendicular to the z-axis. Okay, that's this case, right? So this one has a maximal variance. Okay, so you can see if the spin is pointing in the z direction or the minus z direction, which are the eigenstates of sigma z, and there will be no variance if you measure sigma z. Okay, but if the spin is in the xy plane, okay, the Bohr vector is in the xy plane, and you measure sigma z, actually you got to randomly up and down, right? You got an equal probability to be +1 or -1. So you have a maximal variance, which is 1. Okay, so that's the example of sigma z, right? Okay, let's consider a less trivial case. Okay, let's consider case how about the sigma x. Of course, there will be also two outputs, +1 or -1, and corresponding the states will be two eigenstates, right? And this one, of course, equals to up and down. This will be up minus down, right? So that will be states. But then the question is, what's the probability, right? Remember, we can write down these states. This one is cosine theta over 2 times e to minus I phi over 2 and spin up, and plus sin theta over 2 e to plus I phi over 2 and spin down, right? And suppose we can write down this as sigma x times x plus sigma x bar and x bar, right? Of course, this can be also written like this one. So if we know this, and then we know that px, let's call this one p plus x, p minus x, okay? P plus x will just equal to cx modulus squared, right? And c minus x will just equal to c minus x, cx bar modulus squared, right? So the question of what is this one? So what is this one? How do we calculate this cx and cx bar? Do we have a way to do it? Okay. There are different ways. So the question is cx equal to what? Cx bar equal to what, right? There are different ways. One way is that we can write down. So method 1. We just write the spin up can be written as x plus x, and the spin down written as x minus x bar. So you insert this one into m, okay, and then you can write down this m equals to and x plus something times x bar, right? Then you obtain a cx and c minus. I leave this one as a way, for you to practice. Okay, you can do this. Can you think of any other way to do it? So there's another way to do it. Okay, you can just say, let's take so method 2. They are actually equivalent, okay? So we know that cx must equal to x, the overlap between the two, okay? The inner product between the two states. the eigenstate x and the state you are measuring the operator on. Okay. So now we just do this one. So this will equal to cx compass, sorry, square root over 2, spin up plus spin down. But now this is a broad state, right? And this one will be just e to minus I phi over 2, cosine theta over 2, spin up plus e to plus I phi over 2, sine theta over 2, spin down. Okay. And now we need to do the calculation. Let me do this one more carefully and step by step so that you know this. Right. So here you have one term, two terms, right? Two terms. Here you have one term, two terms. So the products of them will give up 4 terms, right? So the result will be, say, 1 over square root of 2. Let's look at the first term. The first one will be up e to minus I phi over 2, cosine theta over 2, and up. That's the first term, right? And then this one times this one, that will be the spin up e to I phi over 2, sine theta over 2, spin down, right? And there will be another term, the spin down state, and then plus, of course, spin down e to minus I phi over 2, cosine theta over 2, spin up, and plus spin down e to I phi over 2, sine theta over 2, spin down. Okay, so that's the result, right? And let me check this one. So this is up and up, so that will give us 1, right? And this one is up, this is down. The two states are orthogonal, so this gives us 0. And this is up and down and up, so that's give us 0. And this one just give us 1, right? So the result after doing this one, so it's just the summation of the two terms, which is just let me say 2 times over square root of 2, and then sorry. So you have 2 terms. So that's 1 over square root of 2 e to minus I phi over 2 cosine theta over 2, right? And then plus e to minus I phi over, so plus I phi over 2 sine theta over 2. Okay. So this is one term, right? And then you can follow the same procedure. Okay. Let me show you what is Cx bar. Just doing the same thing. Okay. But what you need to do is to change this one, change this plus side to be minus side, and then you do all the same thing, right? So you can say that if we do that, you can say that this one will change to be minus side. This one will change to be minus sign, right? But these 2 terms are 0. And this term will not change the sign, okay? We will change the minus sign, sorry. So this will change, this will change minus sign, okay? So then the result will be 1 over square root of 2. This term, that's e to minus I phi over 2 cosine theta over 2. And now this term is, the next term will be minus sign, right? Okay. So you got a Cx and a Cx bar. And now we can calculate the probability. Okay, so what is the probability? Okay, so P plus X is just equal to Cx modulus squared. You put this term right here. Okay, so what's the result? So it will equal to 1 over 2, of course. There will be cosine theta squared over 2. There will be sine theta squared 2, sine squared theta over 2, right? And there will be a cross term. That will be sine theta cosine theta. So there will be 2 sine theta over 2 cosine theta over 2. And then cosine phi. Right, so that's a cross term. Right. So this one is just 1. This one is just sine theta. So the result is just 1/2. 1 plus sine theta cosine phi. Of course, another term is p minus x. That will be 1/2. 1 minus sine theta cosine phi. Okay. Now we can calculate the average. So that will be px minus p minus x. So the difference of the two, that is, of course, is just the sine theta cosine phi. Okay. And sigma x squared averaged is just 1. And the variance is just a difference. Just 1 minus sine squared theta cosine phi squared. So that is actually 1 minus mx squared, right? So the x component of this broad vector squared, okay? Right, so we obtain the results of this sigma x. Very similar, you can do the same thing for sigma y. So I will not repeat this one. So for sigma y, you're going to have 2 outputs, +1 or -1. The states will be y that equals to spin up plus I spin down over square root 2, and the minus y equals to plus up minus I times spin down over square root 2, okay? And the probability py that equals to 1/2, 1 plus sine theta sine phi. Okay, I need this one for you to calculate as exercise. Another is 1 minus sine theta sine phi. Okay, and then you have the average is just the sine theta sine phi. This is nothing, actually, just the y component of my. And the sigma y squared, of course, is just 1. And the variance is just 1 minus ny squared. Okay? So now put all of this one together. You got a very interesting results. So sigma x, sigma y, sigma z, they have average the expected values just equals to sine theta sine cosine phi sine theta sine phi and the cosine theta. What's this? That's very interesting, right? So this is just the 3 components of the Broca vector, and all of a sudden we got a physical meaning, right, for the state. For the state m that equals to theta phi, that equals to e2 minus I phi over 2 cosine theta over 2 spin up plus e2 I phi over 2 sine theta over 2 spin down. Okay. So now this one has a meaning. This is the Broca vector. So it is just the spin polarization, the spin averaged divided by, of course, h bar over 2. So that we make it into the unit. So we call this one is the spin polarization. So basically, it's just the direction of this spin, right? So this states now finally got some very straightforward physical meaning. So that means if you measure this spin, okay, along any directions, and do this one many times, and then look at the average, and the average will give us the spin polarization along the direction that is the same as this Broca vector, which give us the Euler angles theta phi, which give us the specific form of this wave function. Okay, right. So that is the very nice thing about this quantum measurement of a spin half. Okay. How about we take a break right here, and then we can consider the evolution of the spin half. It's also very interesting. Okay. All right. So we're going to take a break. So now let's consider evolution. Okay. Of a state. Okay. So if we have Hamiltonian, in general, so let's write down this as B dot S, right? And this B just equals to, minus GE mu B and S over H bar, right? So that is the kind of a frequency equivalence of this, magnetic field. Okay. Right, so this B has the dimension of frequency. Okay. And so we're going to say that if we have a psi that equals to, for example, initial state is e to minus I phi over 2 cosine theta over 2 and spin up plus e to plus I phi over 2 sine theta over 2 and spin down. Okay, so which is a state like this one. Okay, right. And then the question is phi t, psi t equals to what, right? So in general, this could be, it's not a difficult problem, but if you're not familiar, it could be a little bit tedious for the calculation. But let's consider a simple case. Okay. Let's consider a simple case. Hamiltonian just equals to say BC times SC. That is actually very simple. It's already diagonal. Right. So in this case, we say that we have a magnetic field just applying the z direction. Okay. So this B is in this direction. Okay. And let's see what will happen of the state. And this one obviously have two eigenstates, right? Spin up and spin down, two eigenstates. With eigenenergy is h bar bz over 2, h bar bz minus h bar bz over 2, right? Okay, so there are two states. So you know that if we have a superposition of these two states, the evolution actually will be very simple. So psi t will be just, this is the initial amplitude, right? But then you need to times e to minus I, this eigenstate. We call this one E spin up, E spin down. Spin up times T over H bar, right? And then plus e to I phi over 2 sine theta over 2 and spin down. And because the evolution, you got another phase factor, that's minus E spin down T over H bar, because this is just eigenstate of the Hamiltonian, right? This is eigenstate of the Hamiltonian. So that's the evolution, right? According to Schrödinger equation, okay? Right? But now you can combine this. You combine this term and this term. So that equals to e to minus I, no, it's phi plus bz times t over 2, right? And cosine theta over 2, spin up. And another term, similarly, is just phi, that's the original phase, plus the E spin down is just H minus BZ, right? So that's gives us BZ times T and then over 2. Okay, and then sine theta over 2 spin down. So what is this state? So this one is just n prime or nt. Okay, let me write down this as nt. What is this nt? Nt is just a new vector that has error angles to be theta and phi plus bt. So it will be sine theta cosine phi plus bzt. Sine theta times sine theta phi plus bzt, and then cosine theta. Right. So what's this state? It is actually, if you plot a circle on this with the same latitude, so the state will be, so this is the new state, new Borel vector, and this is the original direction. Okay, so this is the original direction, and this is the new direction, and this angle is the change during this time, and the change of this one. Remember, this one originally is say is phi, right? And this one is bz times t. Right. So that means if you look at this Borel vector, so this Borel vector, this m, actually is precessing about the z-axis with angular frequency omega equals to bz. Right. So that is a very interesting. Okay. And you can see that since this z direction is actually just chosen arbitrary, right? You can choose this direction as the z direction. So suppose we have a magnetic field applied, you can always set up your coordinate system so that the B field direction is just taken as the z direction. Okay. So that means the spin will always be precessing about the B field. Okay. Right. Z is can always be chosen as along, right? So we just define this direction as a z direction. So that means the spin, okay, is precessing. Actually, it's about the B direction, right? So you can see that this spin dynamics actually is very simple. Okay, it's just like in classical mechanics, if you have a torque, if you have a top, okay, a top precessing about the torque, right? In classical mechanics, okay. So the spin is something very much like a torque, okay, a top, okay. And then, so that's probably one of the reasons that we call this one spin, okay, right? So then we said that maybe this one tells us what is spin, okay? And very often, you know that if you have a top, right, something like right, this is a top, okay, a spinning object, okay. And if you have a top like this one, and then you can apply a torque in this direction, and then you're gonna have a precessing, right, of the top, about the torque, right? This is classical mechanics. So the question, so is a spin just spinning top? Right. The first of all, it looks like it explains the precession. Okay, and also you know that there's a relation between this magnetic dipole moment and the angular momentum operator, right? Looks like also okay. And so this gives us some kind of hint. Maybe yes, we can interpret a spin of electron. Is that this electron is just a spinning? Okay. So if we put the charges, so you can put a charge right here. Okay. And then if these charges are spinning, you're going to have a current, right? And if a current, then you're going to have a magnetic dipole. So that is what we usually, tell students that this is a kind of intuitive understanding of why the electron has magnetic dipole, why the spin has angular momentum. But actually, this picture, unfortunately, fails. This picture doesn't work. Let me show you why, okay? First of all, this mu equals to GE times mu B times S over H bar. And the GE does not equal to 1. And indeed, GE is about 2. And to explain this G equal to 2, and Dirac in 1928 come up with this relativistic quantum mechanics that give us the result G equal to 2. But actually, it's not exactly 2. Okay, it's G equals to 2, 0, 0, 2 something. Okay, there's kind of one, 1 out of 10 thousandths correction. So the correction is explained by the QED. Okay, with precession actually 10 to minus 8. So this is the most successful prediction in physics theory. Okay, we get 8 or 9 digits agreement between the theoretical calculation and experimental measurements. And how do we measure this one? By the way, and GE is measured precisely using spin resonance. Okay, so if you have a spin is rotating, precessing, you actually got a magnetic field that's an AC magnetic field with this frequency the same as the precessing frequency of the spin. And we know that experimentally, the frequency can be measured very, very precisely because it repeats many, many times, right? So you can measure the frequency very precisely. So that's why we can go this number, GE, to very high accuracy, okay? And then we can compare to the QED, the quantum electrodynamics, which can calculate these corrections due to the vacuum fluctuation. So due to the vacuum fluctuation of the EM field. very precisely. Okay, right. So this is the first reason that you cannot just take this spin as a charge current, rotating. Okay, because the relation between the magnetic dipole moment and the angular momentum does not fit into the theory for moving current. So actually, the real reason for this one is that is Qm plus relativity give us the spin. Okay, so this is the first reason that we cannot take this one simply as a current. Secondly, is that this spin equals to half. So that means you have no way to write down the wave function. Let me show you why. Okay, suppose you have a wave function, you can say that this SC just take values plus or minus half, right? And suppose we have a wave function m phi, that will be e to I m phi. That will be e to I phi over 2. And you can see that then you have the wave function at 0 and 2 pi. They are not the same. They are different by a factor -1. Right? So that means you cannot have this one to be single valued. In real space. So that means the spin must be internal states. So actually you can see that if you have a rotation, remember if we have a rotation of the spin by 2 pi degrees, let's say theta phi, and then change after t equals to 2 pi over bz, for example, the state will become theta and phi plus 2 pi, right? Okay, this one actually equals to e to minus I phi plus 2 pi over 2, and then cosine theta over 2 spin up, and plus e to I phi plus 2 pi over 2, sine theta over 2 and spin down. So look at this one, e to I 2 pi over 2 is just e to I pi, right? So that gives us a minus sign. So that's nothing but just phi over 2 cosine theta over 2 spin up plus e to I phi over 2 sine theta over 2 spin down. It's nothing but just a minus sign times theta and phi. Right? So you can see that a 2 pi rotation just give us a -1 global phase factor. To the state. Right. This is a very strange. So you know that if we have real space wave function do a 2 pi rotation, the wave function will not be changed, right? But for spin half, if you do a 2 pi rotation, you got a minus sign. Of course, it's a global phase factor, so it does not change. So sigma x, sigma y, sigma z, all of these things is unchanged. That's fine, okay? So if you do the measurement, the period of this evolution is still 2 pi over bz, okay? That's all normal. But if you look at the wave function, if you really kind of concerned about the wave function, you find there's a -1 sign right here, right? So it's very strange. And this minus sign actually is deeper related to, the spin of this this half spin, okay? So this minus sign, by 2 pi rotation of a spin half, okay? We're not does not change the measurements like a sigma x, sigma y, sigma z, so on and so forth, any kind of measurements, but still has important and profound consequence. So I will not discuss the details right here, but one of this is called a Kramer's degeneracy. Okay, that's one of the examples. Okay, all right. And then you wonder, if I have a spin half, can we have a spin 1/3? Can we have a spin 2/3? So on and so forth, right? Let me give you just the answer, okay? I will not prove right here. So if you want a proof, you can try to register or sit in the course 4021, okay? So in the 3D space, that's important, okay? In the 3D space, and this S has to take a value 0, half, 1, half, third half, 3 halves, 2, and so on and so forth. You cannot take other values. The reason is because of the symmetry of a 3D space. Okay. So there's no possible values, other possible values for the spin or the angular momentum quantum numbers. Okay, to take it can only take a 0 value or half or integer. Okay, this is an intrinsic property of a 3-dimensional space. Okay, it has nothing to do with any other. So it's very robust. Okay? This is one thing. And secondly, so that means you can have only 2 kinds of particles actually. So if S equal to a half, okay, 3 halves and so on and so forth, we got a so-called fermions. Okay, for example, you have an electron, a positron, a proton, neutron, a positron, a mu, and so on and so forth, right? And for the, if S equals to integer numbers 0, 1, 2, and so on and so forth, we call this one bosons. For example, the photon, W and Z, okay, right? A gluon, okay, graviton, if there is any, right? So on and so forth, okay. So these are called bosons, and bosons always have integer spin, and fermions always have half integer spins, and the reason is also related to the symmetry, okay. So to have half integers, the particles must be fermions, okay, right? So for all of this one, so what is the spin? So what is the spin? Okay, so it is caused by the symmetry of 3+1D space-time. Okay, it's not the spinning current. Okay, so these are 2 things, 1 and 2. Okay, so a spin is not a spin current. It is actually stems from the symmetry of the 3+1 dimensional space-time. Okay, all right. And now finally, let me show you the precession and general case. Right, so we have claimed that spin precession is that and this S averaged precessing about B direction with angular frequency omega just equal to B for the Hamiltonian. Now let me prove this one. Okay, proof. So method 1, solving the Schrodinger equation. Okay, this is exercise for you. Try it. It's worth trying. Method 2. Remember, if we have theta phi, we can get the sigma x, sigma y, sigma z averaged just equals to sin theta cosine phi, sin theta sin phi, cosine theta, right? Remember this. So that means if we know this, we also know this, right? So now we just need to calculate this one. So what we need to do just to look at this, the average of this one. Let's look at this. Okay, what is this? If you still remember what we had learned a little bit before, probably you don't have very strong impression, but we have determined that if we have any quantity, so the time derivative of its special values, say for example Sj, can be actually written as the average of this Sj operator and Hamiltonian commutator, right? So we use that one to derive, for example, the Ehrenfest theorem. And now this Hamiltonian can be written as a summation of k, bk, sk, right? Okay. And now this one can be written as so summation of k equals to x, y, z, and the average of this Sj and sk commutator times bk, right? And now this one satisfies the commutator, that is the, if it's x and sx, sy give sc, sy and sc give you sx, and sc and sx gives you sy. So what's that relation? That's nothing but just the product, actually, the cross product. So we can write down this as I h bar s L and then times bk epsilon jkl. What is epsilon jkl? Epsilon jkl actually. So let me give you this epsilon jkl just equals to 1 for x, y, z, minus 1 for y, x, z, else just 0. Okay. And for this, and also of course for the cyclical. Okay. So this, because if this is x, y, that gives x, y, z, right? If it's y, z, that gives y, z, x. Okay. So this one is just called is a unit antisymmetric rank 3 tensor. Don't care about this name, okay? It's useless at this point. So basically, if this is just form a cyclic right-hand rotation, it's x, y, z. You call this one epsilon jkl, okay? It's 1. If it's left hand, say yzx, sorry, yxz, that's minus 1. Or if you have repeated indices, it's just 0, okay? And then this one, if we know a little bit of mathematics, this is nothing but just IH, B cross product with this average, okay, sorry, average of SL, sorry, of S. And the J component. So with all of this one, so you compare this side and this side, you got a result that's d over dt S just equals to B cross S. So this is nothing but just the the precession equation for S around B, right? So now you can see that since you know this, you know the precession. So this is Bloch vector is precession brought B with angular frequency, this one. So you know this result is simply just given by precession, right? Okay. So that is a very elegant proof of this result that if you have a magnetic field pattern along any direction, so the Bloch vector, which is the same as the exponential values of the spin operators divided by h/2, we're just precessing about the B field with angular frequency given by this B, right? Okay, is that all right? So you probably, I don't know if you know a little bit about this one. So if we have, if we have, for example, let me give you a little bit explanation of this one. So if you have two operators, two vectors, like A plus B equals to C, right? So basically, we write down this as I, J, K, A, AX, AY, AC, and BX, BY, BZ, that equals to C. Okay. So this is the determination of this one, right? So this is and this determination is just given by E A times AB and let's say IJK. Okay. So that's the definition of the order product. In case you're not very familiar with this one, so that's C is just equals to EI and AJ and BK times equation IJK. So this is just the definition of the determinant, okay, of a matrix. So 3 by 3 matrix. Okay, let me call this one EX, EY, EZ. Okay, right. So using this one, so we got this formula. Okay. So actually, it's this formula. All right. So that's more or less about the spin states, right? So now we have a state. Okay, has an orbital wave function, right? For example, psi m l m r theta phi, right? And spin, for example, 1 0, right? Like a matrix. So now a particle can have both of this one. So we can say that if you have a combination, okay, the state, right? For example, we can have M, L, M, and now we also have MS. Okay, so we need 4 quantum numbers, okay, to denote, say, an eigenstate of a hydrogen atom, right, for example. And this MS equals to plus or minus 1. It's the spin quantum number. Okay. Right. So now you can see that suppose the energy EMLM just equal to EM, right? For M equals to 1, 2, 3, and so on and so forth. And L we know that equals to 0 or 1. At the most is M minus 1, right? And M equals to 0 plus minus 1. At the most is plus minus L. And MS is equals to plus or minus half. So we have this 400 numbers denote state, but the energy only determined by the M. So given the M, we have a different choice of L, M, MS. So the degeneracy is given by M squared times 2. And this 2 comes from the spin half degrees of freedom, okay? Right, so that's why for the electron, in the atom, so the one S shell actually has not one state, it has 2 states, because there's a spin, right? So if you really want to write this in a wave function, okay, so wave function, right? Remember the spin half has no real space wave function. So you cannot write this one just as something like say, so you cannot write down this, say, for example, MS equals to psi MS XYZ, okay? There's no such kind of notation of this one, okay? So you have to use instead, so MS equals something like, say, A and B, 2 times 1 matrix is fine, okay? Okay. And then for the state M, L, M, MS, we know that these parts denote a wave function, okay? So it can be written as some kind of, so psi M, L, M, R, theta, phi. That's a real space wave function. And then times a chi, MS, right? So this one is just, so this is a function in 3D space, and this one is 2 times 1 matrix. Okay, right? For example, let's say 210 plus half. That can be written as psi 210 r theta phi. Okay, 10, and this one of course can be also written as 210 r theta phi 0. It's a 2 by 1 matrix as a function of so it's a 2 by 1 matrix as a function of r theta phi. That's 3D space, right? 3D coordinates. Okay. You can also have other examples. Okay. Let me write another example. You can also have, say, you can have superposition. For example, you can have the 2, 1, 1, minus 1, and plus 2, 1, 0, plus half. Okay. So this is superposition. So this equals psi 2, 1, 1. XYZ. If you want, it's r theta phi. It's also okay. And 0, 1, and plus psi 2, 1, 0, XYZ, and 1, 0. You can write down this combine into just the summation of a 2 by 1 matrix. The 2 by 1 matrix is still 2 by 1 matrix, right? So it's equals to psi 2, 1, 1. X, Y, Z. And this is a psi 2, 1, 0, X, Y, Z. Okay. So it's still a 2 by 2x1 matrices, and with each matrix elements just give a real space wave functions. Okay, right. So this is states of write down examples of write down the wave function. You know that depends both has both orbital parts and the spin parts. Okay. So now this nothing is operators, and expression values. Okay, in this one. So I just give you a few examples, and then you can say that. So in general, the state per psi can be written as per psi plus x, y, z, and 1, 0 plus per psi minus x, y, z is a real space wave function, and 0, 1. So it can be written as per psi plus, per psi minus. Okay, and this per psi plus minus are just two certain wave functions defined in the three-dimensional space. Okay, and the spin is denoted by a matrix. Okay, so in general the two could be different. Okay, so let's calculate consider a few examples. Right. Let's look at for example, the matrix, the expression value of angular momentum, the orbital angular momentum. That's an orbital state. Right. So this one, of course, equals to per psi, and L, x, and per psi. So let me write down this first. This is Lx, and this will be per psi plus. This is per psi minus. The Hermitian conjugate, you take the transpose first, and then take the complex conjugate. Right? So there will be, but this one acting only on the wave function, does not act on the spin. Okay? So this one is kind of a diagonal. So you can write this as two terms. Okay? And then plus another term. Okay, so that's the way how we calculate the average or the expression value of the orbital operator. Okay, so you can see that this orbital operator acts only on the real space part wave function. So it does not change the matrix. Okay. So for example, Lx acting on this per psi plus, per psi minus, actually just equals to Lx acting on per psi x, per psi plus, and Lx per psi minus. Okay, does not change the matrix. Okay, this is one example. Let's consider another example. Let's look at for example, Sy. Okay. So Sy equals to per psi, Sy and per psi. That equals to, say, per psi plus complex conjugate, per psi minus complex conjugate. And Sy is a matrix that's 0 minus I h bar over 2 plus I h bar over 2 and 0. And this is per psi plus, per psi minus. Okay. And this one acting only on the spin. That means just do the matrix operation. Okay, no action on per psi plus, per psi minus. Okay. So the result will be, so this one will be per psi plus complex conjugate, per psi minus complex conjugate. And now, so you can write down this as h bar over 2, can put right here, okay? So you multiply this matrix on this two as if you take a per psi plus and per psi minus just as two numbers. And this will give you, you do the exchange of the two, and then times minus I on the, so you got minus I percent minus, plus I percent plus. Okay, and then you do this one, and this will give us h bar over 2 minus I, and then percent plus complex conjugate, percent minus, percent minus, and integration over the space, because we are doing the inner products, right? And then plus I h bar over 2, and percent minus comes conjugate, percent plus, and d, and do integration, right? So that's the result for the spin operators. Okay. You can also have a combination. Okay. Let's consider, for example, example 3, Lx, Sx. So you have two terms. One is the orbital operator, another is the spin operator. Okay. So again, this one equals to Sx can be written as h bar over 2, h bar over 2, 0, 0. And this one is percent plus, percent minus. Okay, so you first do the matrix operation first. That's a spin operator. So that's Lx. This way you just exchange them and times h bar over 2. Okay, so the result is going to be h bar over 2, okay? Percent plus Lx percent minus and dr, and the plus h bar over 2 percent minus complex conjugate Lx percent plus. Okay, so that's the result. So you do the operation. So this Sx, you know, is the matrix operation, and Lx acts on percent plus, percent minus. Okay, so this is the way to do it, right? So as an exercise, I ask you to show that so this Lx Sx actually equals to Sx Lx. If we change the order, the result is the same, okay? Because these are two operators acting on different parts of the wave functions. So that means you can do this one first or do that one first. It doesn't matter, okay? Check it. Okay. And also there's another interesting problem, you know, in the lecture notes for you to do. Okay. So that's another access problem. Okay. So that I think that will be interesting as well. Okay. So this is more or less we have for the spin. Okay. There are many interesting things about the spin, especially general spins, that have not been covered in this short introduction of spin half. Okay. And the spin half problem actually is important these days, because if you look at the quantum information, for example, you know that the building block of quantum computing, quantum communication, and so on and so forth, they are all so-called qubits. And the qubits is actually a state, is an object that has two states, you know, representing 0 and 1 as in a classical computer, but now we have superposition. Okay, so the spin half is a natural qubit. Okay, so studying the spin half and its operations, its evolutions, okay, and its geometrical pictures of a lot of interest, and also it's a lot of fun. Okay, all right, so that's all we have for this course. Okay, so if you have questions on the spin half, you know, please just you know, write it in the chatting room, or if you have more general questions about the whole classwork, and you can ask right now, or you can also ask say on Friday or anytime. Okay, send me an email or ask in the WhatsApp group, and so you know, You can also ask me questions after the examination. Okay, don't just prepare this one for the examination, because quantum mechanics is so important and so interesting. Take this as a lifelong learning. Okay.